Welcome to this presentation on contextual dispatch. This is a new technique we developed for JIT compilers to specialize functions to dynamic contexts. I would like to start this presentation with the example that got all of this started. We are currently trying to develop a JIT compiler for the GNU-R statistics language called RJ. And of course, since we're developing a compiler, we want to know whether it's actually improving the performance of programs. So we need programs to test this. One of the examples we used was this implementation of a Mandelbrot set. And I have elided all of the details, but what is interesting is this parameter n, which is passed to the function and then used to bound the number of iterations. Now, what kind of values can we pass to this Mandelbrot function? Well, we can pass it the number 3, which is probably pretty much what was intended here. On the other hand, we can of course also pass it a more complex expression. For example, this expression that first prints high and then evaluates to 3. And the interesting thing here is that this expression is not going to be evaluated up front, but instead R is a lazy language. So this expression is evaluated when the callee, the Mandelbrot function, accesses the argument n. So the printing happens while the function is already being executed. Now we can go further. I have here a downright evil function. This function reflectively walks the call stack, grabs the environment, the call frame, which is 1 above, and removes the binding n from it. If I pass an expression that calls this evil function to the Mandelbrot function, this means the local variable n is going to be removed from it while the function is being executed. If we look at this from a compiler's perspective, this is what happens. The argument n is actually passed in hot. Its effects only happen once we evaluate it, once we look at it. So effectively, all the effects of these arguments are part of the while loop because the evaluation happens as the first thing when this loop executes. Now, if we think about this from the point of view of a static analysis, of a program analysis, then as soon as this unknown effect happens, all the program analysis state gets tainted and effectively stays so for the rest of the while loop and for the remainder of the Mandelbrot function. In other words, any kind of non-trivial static analysis on this Mandelbrot function is doomed from the point where we access the n parameter. Here is a question. Probably most promises that are gonna be passed to this Mandelbrot function, they're completely benign. They will be the number 3, say, or something like that. But, well, who knows? They could be anything, so who knows? Well, who knows is actually the caller. The caller knows at the call side we know what we're going to pass to the function. And that's the main idea. If we think this true, then it seems there are actually 2 completely different situations here. There's the situation where we call the Mandelbrot function with a completely benign expression, say the number 3. In this case, we should be able to compile a version that does not need to deal with all the reflectiveness, that does not need to be aware that n could actually have any effect. On the other hand, if we call the Mandelbrot function with this evil expression at the bottom, then we really need to be sure that the version that we call is able to deal with any kinds of effect happening within the while loop. And then there's a third class in the middle where we're not actually sure. So the name x, it could be bound to something that is going to evaluate with effects. It could be bound to an expression which is already evaluated or which is going to evaluate without effects. So in that case, there needs to be some sort of a dynamic check to decide. So now if we start to generate multiple versions of the same function, of course the natural question is which one to invoke. And our solution to that question is what we call a context. So in R, a context is basically a property on the program state. And we have different properties that we detail in our work. For example, we have Boolean flags. Let's say if we know that an expression is not reflective, then that's just a yes or no flag. On the other hand, we have also types. The types could, for example, say that the first argument is an integer. Then we also check for shapes. In R, every value can be a vector. So a scalar is basically a vector of length 1, and we have special tests for that. Then we also encode quantities. For example, any argument in R is actually optional. So the number of arguments that a particular call site passes is also noted in the context. The second requirement for contexts is that they form an efficiently comparable lattice. And for example, if we were to test the types of the first two arguments, and in particular we want to know whether they're ints or reals, then we would use the lattice that you can see on the right. Basically, for each type, it can be either int, real, or anything else. And then we take the product of these two lattices, which forms again a lattice that we can use to order the specialization of different functions. Now we have introduced contexts, and the question is, of course, how exactly do they help us choose the right version of a function? For that, I want to introduce the notion of current contexts. A context is simply called current if it currently holds. So trivially, for example, the top context, the any context, is always current. But now you can imagine that, of course, a VM will start to test more and more things, and this will yield a smaller and smaller approximation of a current context. Now suppose I have such a witness, such a current context C, then when I'm about to invoke a function f, I can invoke basically any function which has a context which is compiled under a context that is larger than the current context that I have picked. And actually, the best approach here is to use contexts which are closed under conjunction. That means that I can take any two current contexts and the intersection will be a more precise current context. As an example, take this invocation where we pass x and the integer 3 to the function f. Now we can already statically say that the second argument is an integer, and we don't know anything about the first argument, so the static contribution here is any int. Then dynamically we can check for the type of x, and in this case, let's say the check returns that x is bound to a real. In this case, we don't check for the second argument because we already know, so the dynamic contribution is real any. We can take the conjunction and we will get a more precise current context, which is real any, int, sorry. So finally, we have all the ingredients ready. We have defined our contexts, we have defined an order of function versions, and we know how to figure out which of these versions we're allowed to call. Now the question is, which one should we pick? So there seem to be different choices and not all of them are equally good. And so the question is how to dispatch, how to pick the best one. And I want to explain this with an example of a possible order of versions that we could have in a function. And this function, of course, always features the baseline version. So this is the unoptimized version of the function that is compiled under the context any that can always be invoked. Then we have a smaller context. And in this case, let's say there is a version that assumes that the first argument is an integer. Then we will add a new version, which additionally assumes that the second argument is non-reflective. This one is again smaller. We have another not comparable version, which assumes that at least one argument is missing. So the caller, let's say this function takes 3 arguments and the caller is going to pass at most 2. Then we have another context and another function version, and here the assumption is that exactly 1 argument is missing, or another one which is that more than 2 are missing. Now, given a current context, the question is how should we pick one of these versions? And the solution to that is to extend this partial order to linearize it to any compatible total order. Like so. Now what we generated is a dispatch table that we can search from left to right for the first matching entry. And this will be the version that we dispatch to. So if you follow closely, then you will notice that the choice of the smallest matching context is actually ambiguous, and this linearization essentially leads to us picking a random one of the smallest possible choices. Let me give you an example of that situation. So here I'm calling the f function with an integer and a double. And let's say I already have 2 versions for this function. One is compiled for integers and anything. The other one is compiled for anything or reals. There is clearly no way to know which one would be better to call. Either of these 2 could be better or worse. So I have 2 choices essentially. I can dispatch to either of those 2 since the result will be correct. Or we have a JIT compiler, we can JIT compile a new version and add it to the dispatch table. And here the best choice would of course be int and real. In RJ we have a heuristic and we keep track of suboptimal choices, and when they happen frequently enough we will do exactly 0.2, we will add a new version to the function. Let's talk about results. We created a benchmark suite with various R programs and compared ourselves against 2 other implementations of R. So this is on the one hand GNU-R, which is the reference implementation. It features a bytecode interpreter. Then on the other hand, we compared against FastR. FastR is developed by Oracle and is based on the Truffle Growl framework. It is a native speculating JIT compiler. Comparing against GNU-R, we're about 1.7 times faster with the range that you can see there. And comparing against FastR, we are slower, though more predictable. So there are less pathological cases in RJ than there are in FastR in our benchmark suite. Of course, these results represent the overall performance of the VM. So this includes speculation, this includes native compilation, and so on and so forth. So the interesting question is actually, how fundamental is contextual dispatch for this performance improvement? And so there are 2 answers to that. The first answer is basically that contextual dispatch was really helpful in developing the VM. There are so many dynamic parts in the R language, there are so many reflective things that can go wrong. So it really helped us that we can specialize functions to certain contexts of benign behaviors. So as a developer, this has been one of the fundamental tools to get the speed up that I showed you before. So that's one answer. And the second, more quantitative answer is that we ran our benchmark with different levels of speculation, and we showed that actually 18 out of 46 benchmarks improve using contextual dispatch. And we also showed that every level of contextual dispatch is significant in at least one benchmark. So how did we measure this? We defined levels where each level adds more properties to specialize with. So for example, we start with types, then we add shapes, then we add non-reflectiveness, we add the number of arguments, and so on and so forth. And then we determine whether the performance is actually increasing throughout the levels. Let me summarize again our technique, contextual dispatch, that allows us to specialize functions to their calling contexts. So first, we define contexts, which are properties that are ordered in a lattice. Then we perform static and dynamic checks to figure out what kind of properties hold at a call site. And finally, we use a linearization of the lattice to select one of the smallest matching versions of a function that match the current context at the call site. If you want to know more, there is on the bottom left, you find the link to the paper and some more explanations, whereas on the bottom right, you'll find the link to the source code and also binary releases.